What is reference pressure and why is it necessary to specify reference pressure? The reference pressure is simply a device that is used to reduce the numerical round-off error in the numerical calculations involving pressure. This reduction is necessary since the differences in pressure are important, and these differences can be small relative to the absolute value of the pressure. For example, in fully incompressible or very low Mach number flows. By subtracting a suitable constant reference pressure, a working pressure is obtained that is less prone to round-off errors. For simulations that use the constant density model or the polynomial density model, the actual value of the reference pressure has no relevance to the calculations. However, when using the ideal gas model, the reference pressure is used. We know that there is density term in the Navier-Stokes equations. How is that modeled? The equation of state model is used to compute the density and the density derivatives with respect to temperature and pressure. There are various methods for this. Constant density, IABWS, IF97. Polynomial density, ideal gas with combustion, real gas, thermal non-equilibrium, user-defined equation of state or EOS. Let us see them one by one. The constant density model makes the assumption that the density is invariant throughout the continuum. It is available for gases, liquids, and solids. What are the IABWS IF97 models? IABWS IF97 is International Association for the Properties of Water and Steam, Industrial Formulation 1997. This model allows you to run simulations of liquid, water, or gaseous steam. These models include calculations of density and other thermodynamic properties. The polynomial density model makes the assumption that the density is a function of temperature only and is available for gases, liquids, and solids. The ideal gas model is available for gases only. It uses the ideal gas law to express density as a function of temperature and pressure. There are also real gas models. Real gas models are used in situations where the gas properties cannot be explained using the ideal gas law. For example, near the condensation point of gases, near critical points, and at high pressures. Real gas models take into account non-ideal behavior such as compressibility effects, variable specific heat capacity, van der Waals forces, and non-equilibrium thermodynamic effects. Star CCM Plus has variety of real gas model. Let us list them here. Peng Robinson is available for gases only. Then Redlich Kwong is available for gases only. Sov Redlich Kwong is available for gases only. Modified Sov Redlich Kwong is available for gases only. Van der Waals is available for gases only. Then equilibrium air is available for air only. IABWS IF97 is available for steam or liquid water. Now, after discussing all material properties models, we come to solvers. First, let us have an overview of both solvers available. The implicit segregated solver solves flow equations in a segregated manner, that is, one by one. In order to link the continuity and momentum equations, it uses the predictor-corrector approach. Another solver is the coupled solver. The coupled solver can be implicit or explicit. It solves the conservation equations for mass and momentum simultaneously using a time marching approach or pseudo-time marching. It also uses grid sequencing, which means an initial guess is computed on a coarse mesh before starting actual calculations. All solvers use the algebraic multi-grid or AMG method. To decide whether to go for segregated or coupled solver is dependent on various aspects. Let us discuss them here. The segregated algorithm uses less memory than the coupled. The coupled algorithm yields more robust and accurate solutions in compressible flow, particularly in the presence of shocks. The coupled algorithm is more robust for high Rayleigh number natural convection. The number of iterations that the coupled algorithm requires to solve a given flow problem is independent of mesh size. However, the number of iterations that the segregated algorithm requires increases with mesh size. Knowing these factors, there are general guidelines for selection. Choose the coupled flow and coupled energy models for compressible flows, natural convection problems, and flows with large body forces or energy sources. If computational resources are not an issue, choose the coupled flow model for incompressible and isothermal flows. Choose the segregated flow model for incompressible or mildly compressible flows. The coupled flow model solves the conservation equations for mass and momentum simultaneously using a time or pseudo-time marching approach. The preconditioned form of the governing equations that the coupled flow model uses makes it suitable for solving incompressible and isothermal flows as well as compressible flows. The model has robustness for solving flows with dominant source terms such as rotation. Another advantage of the coupled solver is that CPU time scales linearly with cell count. In other words, the convergence rate does not deteriorate as the mesh is refined. Let us discuss various options with this model. First are the integration options. The model has two integration options, implicit and explicit pseudo-time integration. When we select the coupled implicit solver, the software adds a coupled implicit node to the solver's node with the option to set a coherent number ramp. If we select explicit option, it will add a coupled explicit node to the solver's node with the option to set a coherent number ramp. There is another selection which is discretization. It will decide the discretization scheme that is used for evaluating phase values for convection and diffusion fluxes. First order, second order, central, bounded central, hybrid, and hybrid BCD are the available discretization schemes. The coupled energy model is an extension of the coupled flow model. Together, they solve the conservation equations for mass, momentum, and energy simultaneously using a time or pseudo-time marching approach. This formulation is robust for solving compressible flows and flows with dominant source terms such as buoyancy,